Here are solutions to homework set number 6 for ECE 461-661 control systems. This homework set looks at finding transfer functions for circuits, mass spring systems, and rotational systems. The first problem is, here's a circuit, find the transfer function from V1 or Vn to V3. Now the approach we'll be using is for capacitors. The current, I, is C dV dt. So the capacitance times the derivative of the voltage is I1. Current in equals current out. So I1 is this current plus that current plus that current. Current from the left is V0 minus V1 over 10. Current from the right is V2 minus V1 over 20. And the current up is 0 minus V1 over 100. All that added together is the current of the capacitor. For I2 is the current from the left, right, and down. So I2 is C dV dt. That's V1 minus V2 over 20 plus V3 minus V2 over 30 plus 0 minus V2 over 200. And finally, I3 is the current from the left plus current up. I3 is C dV dt. That's V2 minus V3 over 30 plus 0 minus V3 over 300. So these are the three differential equations that describe that circuit. To find the transfer function, we'll put it in matrix form, meaning state space, throw it in MATLAB, and find the transfer function. So first what I do is plug in C, solve for the derivative, group the terms, express these in matrix form. So if I make the states V1, V2, V3, kind of what I like doing is just reminding myself, first column is times V1, second column times V2, V3, and V0, or Vn. So the first equation, SV1 is 10V0 minus 16V1 plus 5V2. Likewise, the second equation, third equation, my output is V3 of the three states. Here's how I pick it out. So this is your A matrix, your B matrix, your C matrix, and D equals 0. Throw that in MATLAB. So MATLAB input the A matrix, B matrix, C matrix, D is 0. Put that in MATLAB, find the transfer function, and poof, there's the transfer function from Vn to V3. If I want to find this transfer function from Vn to V2, just change the C matrix. I want to pull up the second state, and notice when I change the output, the poles stay the same. Poles are energy, that's how the energy dissipates. Changing what I measure doesn't change how the energy dissipates, so the poles stay the same. The zeros depend upon what I'm measuring. The zeros do change. That's one of the reasons in this class we kind of ignore zeros. We just focus on poles. Poles kind of tell you worst case, the energy dissipates in 4 over this pole. If the total energy dissipates in that much time, whatever I'm measuring has got to reach steady state in that much time. Problem 2. Here's another RLC circuit. To come up with the dynamics, for capacitors, I equals C dV dt. For inductors, the voltage is L di dt. So the voltage across this inductor, V1, is the inductance L times the derivative of I1. Again, make the states, the current through the inductors, voltage on the capacitors. That tells you the energy in the system. The change in energy, 0.1 SV1 is the voltage on the left, Vn minus voltage on the right. This voltage is V5 plus this voltage. That's 30 times I1. Second inductor, V is L di dt, so V2 is 0.5 SI2. Voltage on the left is Vn minus 10 I2. Voltage on the right is V4. Third inductor, V is L di dt. Voltage on the left is V4 minus 20 I3. Voltage on the right is V5. Then the capacitors. I4 is current in minus current out. That's I2 minus I3. For this capacitor, V is I equals C dV dt. I is 0.25 S V5. That's I1 plus I3. So these are the 5 differential equations that describe that circuit. Grouping the terms, putting in matrix form. Here's your A matrix. Here's your B matrix. A and B. The C matrix, if my output is V5, C pulls off the last state. Throw that in MATLAB, find the transfer function, and poof! This is the transfer function from Vn to V5. 5 poles, I've got 5 energy storage elements, 5th order system. If I want to know what initial condition makes the energy decay as quick as possible, what makes it decay as slow as possible, that's an eigenvalue eigenvector question. I have a 5x5 matrix for A. I have 5 eigenvalues, 5 eigenvectors. The fast eigenvector, well, the fast eigenvalue decays as the fast eigenvector. To make this the initial condition, that decays as e to the minus 299t. If I make this the initial condition, that decays as e to the minus 0.23t. And kind of notice the eigenvectors. This is I1, I3, I2 primarily. I1 decays as e to the minus 299t. I3 decays as e to the minus 99t. I2 decays as e to the minus 19t. That kind of makes sense. If you look at the circuit, I've got this inductor. This current dissipates as heat through that resistor. This dissipates through heat through that resistor, and so on. So the current through the inductors decays quickly. Those are the fast eigenvectors. The voltage on the capacitors, that's these two and those two. Those are the slow modes. If both capacitors are charged positive, that decays really slow. Kind of go differential, 1 plus, 1 minus, decays a little bit faster. Going on to problem 4, mass spring system. If I have a mass spring system, what I would do in this class is draw the circuit equivalent. I've got 3 masses, I have 3 voltage nodes, x1, x2, x3. Each mass has inertia to ground. So I'd add, first thing I do is add the inertia to ground, ms squared, ms squared, ms squared. Then add everything else. Between mass 1 and ground, I have a spring of 5. I have friction of 2, that's 2s. I have a force. As force is positive, x1 increases, so the arrow goes up. Between 1 and 2, I have a spring of 6. Between 1 and 3, I have friction of 3s. Between 2 and 3, I have a spring of 10. And that's everyone. So here's the circuit equivalent. Once you get the circuit equivalent, write the node equations. The shortcut is at node 1, all the admittances attached to the node. Again, these are admittances, not resistances. There's a difference. All the admittances attached to the node times x1 minus the admittances between 1 and 2 times x2 minus the admittances between 1 and 3 times x3 is the current to the node. Likewise for node 2, likewise for node 3. So these are the differential equations that describe that circuit. To find the transfer function, I'll put this in matrix form. To do that, solve for the highest derivative. Set the states as position, velocity. The derivative of position is velocity. The derivative of velocity is acceleration. That's these equations. So for example, the first equation, s squared x1 is minus 5/3 sx1, that's this term, minus 11/3 x1, plus 2x2, there it is, plus sx3, plus 1/3 f. Likewise, second equation, third equation, throw that in MATLAB, B matrix, C matrix, D matrix, input into MATLAB, find the transfer function, and there's the transfer function of this mass spring system. Mass spring systems can have complex poles. To get the step response, plot the step response, and kind of see what the answer would look like. Here's the dominant pole. It should settle out in about 4/0.5, about 8 seconds. And as we see, in about 8 seconds it settles out, plus there's some oscillations on there. That would be this pole right there. is pretty slow as well. Another mass spring system. First, draw the circuit equivalent. I've got 4 masses. I've got 4 voltage nodes. Each mass has inertia relative to ground. If you put them in series, that violates Einstein's theory of relativity. Mass has mass regardless if the rest of the universe doesn't exist. Then between mass 1 and ground, spring and friction. Between 1 and 2, 2 and 3, 3 and 4. Here's the force input. Write the node equations. At mass 1, all the admittances attached to the node times x1 minus the admittances between 1 and 2 times x2 is the current to the node. Node 2, node 3, node 4. Throw it in matrix form. Again, it's kind of a check. This is the spring matrix. It's a function of k's. Here's the friction matrix, function of b's. Negative on the diagonals. Throw that in MATLAB. B matrix, C matrix. Find the transfer function, and poof, there you go. This is an 8th order differential equation. But look at the eigenvalues. The dominant pole is right here. It should oscillate at about 0.77 radians per second for a really, really long time. Take the step response, and that's the slow mode, just oscillating. Finally, for a rotational system, kind of long assignment here, I've got 3 inertias, draw 3 masses relative to ground. Now start filling them in. At mass 1, I've got a spring and a torque. Here's the torque, here's the spring. I get to a gear. This is a 1:5 ratio. What this says is 1 theta 1 is 5 theta 2. If theta 2 turns once, theta 1 turns 5 times. Takes you to node 2. Node 2 has inertia and a spring. Takes you to gear, the second gear. 1:5 ratio takes you to theta 3. I've got inertia and spring. So there's the circuit equivalent. Next step is get rid of the gears. When I go through a gear, I transform as the turn ratio squared, times 1/5 squared. So all this is times 1/5 squared. Everything over here is times 1 to 5 times 1 to 5 gives you 1/25 squared. Let's see. So I have my 3 differential equations. Ones that just have 3 nodes. All the admittances attached to the node times theta 1 minus the admittances between 1 and 2 times theta 2. Second node, third node. Solve for the highest derivative. Put it in matrix form. Throw it in MATLAB. And poof, there's your transfer function. Eigenvalues or poles. Here is the slowest eigenvalue. Take the step response. This is oscillating at 0.1 radian per second. Decaying is e to the minus 0.0011 t. And that is homework set number 6 for ECE 461. Point behind the homework set is whenever you see a transfer function, think about the different systems. If you have real poles, that's like an RC circuit. Complex poles, RLC circuit, or mass spring system. The math doesn't care. Any system that has the same transfer function behaves the same. Just kind of gives you an idea of something to think about when you see problems later on in the course. Homework set 6 for 461.